Good afternoon, everyone. So we will be discussing this course ES661, Probabilistic Machine Learning. I'm assuming that many of you have already taken the course Machine Learning because that would be considered as a prerequisite for this course. We would unfortunately not be able to repeat all of the content which we covered there. So I'll first quickly walk through some of the logistics of the course, followed by the course contents. We have 4 teaching assistants. Zeel, Sarth, Madhav, Haiku, if you could raise your hands if all of you are there. So Zeel, Sarth, Madhav and Haiku. The course timings are Monday and Thursday. So Monday 3:30 to 4:50 and Thursday 2 to 3:20. We are living in a quantum universe. So the question was, is there a possibility to change? I think you'll have to first internally communicate with the set of students and figure out something. So for that, the first thing you'll have to do is to join the course via the Slack invite. So some of you had already done this, but I had given an incorrect link. So that was leading you to some other Slack account. So I'd request you to again click on the Slack invite and you'll be joining on the Slack. All the communication going forward from today onwards is going to be on Slack. Right. So we'll be covering a few topics such as Bayesian inference, estimation, sampling, approximate inference, models, applications. Right? And when we'll try and see all of these topics in today's lecture. So the way I've tried to design today's lecture is that this can be used as the first lecture as well as the last lecture. So today we'll try and do a full overview of the course. Some of the things we may not be able to understand the maths behind it, but at least we'll try and understand the intuition. By the end of the course, the same slide deck we can use and understand it as a refresher. I think the most important thing in which everyone would be interested is the grading policy. So we'll have 3 quizzes, 12% each, and the quizzes would be synced with the 3 exams. We'll have 4 assignments, roughly 8% each. Some could be 7, some could be 9. These would be programming assignments, and they would be followed by a Viva. So not just code would be run, but we'd also be asking certain questions in the Viva. We'd want the total number of groups to be 20. So depending on the number of students who are there in this course after the add drop, we'll tell you whether the group size is 2 or 3. Right? The ideal group size that we're looking for is around 20. And we'll have the following rubric for grading the assignments. The correctness of the code, of course. Then the quality of the code. Are you making use of good software engineering practices, such as maybe annotating well, using classes where appropriate, using tests where appropriate, reusing code via functions, and then some presentation and conceptual understanding. You may have solved everything correct, but if you're not able to explain, you should not be getting the full marks. And each assignment would be for 1 week, right? And this will be a hard deadline. We have also given some tentative schedule. So assignment 1 would be roughly released around 10th of August, due 18th August. Assignment 2, so we'll give due consideration to the fact that the course is just starting. Right? So the assignments would not be asking you very difficult concepts in the first assignment in that regard. The second assignment around 21 August. So we have tried to uniformly space the assignments, quizzes throughout the semester so that you don't get loaded at any one point of time. So 21 August to 28th August, 14th September to 21st September, and 30th October to 6th November. So again, while designing this course policy and the grading, one thing which I'm trying to keep in mind is that by the time of your end semester or the last exam, you already know mostly what you'll get in the grade, what grade you'll get, because most of the evaluation would be done. And I'm not a fan of keeping a lot of things in the last week. So if you notice the things, the assignments are completed by 6th of November. The last classes are in the last week of November, right? 23rd, 25th November, something like that. But by that time, the assignments would have been finished. So roughly 32% grades gone, done. And 2 quizzes are done. So 32, 20, and 12, sorry, and 24. 56% marks already done here. The project would be 27%. And this is also, I'm saying that the number of groups that we're looking for is around 10. So based on that, we decide whether the group size is something between 3 and 5. And we are keeping only 2 phases for the presentation. So the first one is around the first week of October, which is worth 10%. The final project presentation, again, I've tried to keep it much before your last cliff. I think last class is around 27th. So 22nd November, we finish about 12%, and the final report is due 24th November, 5% marks. Right, so if you see in the last week of the course, you will have the end semester, which is or the final semester exam during that slot, and you just have the project presentations to be completed. We will also be creating an interactive article, which would be Streamlit, Hugging Face kind of an article, due 15th November, but you're free to submit it much earlier than that. Right? Encouraged to submit much earlier than that, because there could be certain concepts which we could pick up and solve it much before 15th November. You don't need to wait till that and then have a pile up of different things to do. Any questions with regards to the grading policy? Happy and happy. Okay, any other logistical questions before we start the main content of the course? So the timings we'll have to have, in this case, Mihir wants to volunteer and he'll figure out some other time slot, which works for everyone. So we can't have even one student unhappy, because the current timings are given by academics. The students are unhappy. So everyone at least knows the schedule. So again, I'm just repeating if you go to the course website, which is, I'll put it up on my main website also. So my name, nipunbatra.github.io/PML 2023. On the home page, you'll see the Slack invite. If you click on this, you would be taken to a link where you can sign up on Slack. Right? All the further communication will happen on Slack. So course timings, we can, as of now, this is the course timing, but Mihir will initiate a thread, and we'll see if something needs to be changed. Okay. Any other questions with regards to the logistics? So we'll have further details on the group sizes once we know the number of students who are left in the course, which is after add drop period. Yes. That would again depend on the number of students who are left in the course. If the number of students if this is the number of students who will be finally taking the course, we can ask for a bigger class. This would be very difficult with this batch size, but I don't know how many will be left after this. But if the timings has changed, we'll have to look into different classrooms. Other logistical related questions? How many of you have done machine learning? Have taken the machine learning course here? Let's first take that. Okay, how many of you have done it elsewhere? You know machine learning? Okay, so I think so anyone who's not done machine learning earlier or doesn't have a lot of background in machine learning? Okay. So we'll see. If needed, we may have to do a prerequisite test for people who have not taken the machine learning course formally, or who haven't, let's say, done the online version and submitted a certificate. We may have to do that, but we'll see. Any other logistical question before we start the lecture? Okay, so we can start the lecture. So this course would be somewhat of a cutting edge course compared to the regular machine learning course. There, most of the things are very classic, very well-known results. Here you'll see that for some things, we will even look at certain blog posts as references, certain research papers as references, and certain interactive articles as references. Right? So it won't be, so some of the content would be very cutting edge. So the first thing I want to start off with is, let's assume, and as I was mentioning, some of the things would be cutting edge. This is a cutting edge example I'm picking up from a blog post. So let's imagine that we have a machine learning problem at hand. We have 3 classes of animals: wild animals, cats and dogs. So in this case, cats are not taken to be and dogs are not taken to be wild animals, or we just assume that the species corresponding to these are not wild. Right? So we want to predict given a new image whether it's a wild animal, a cat, or a dog. How do you think we will go about this? In the machine learning sense. Okay. So Mihir says that we should be training a CNN, and we'll do a quick review also. Why a CNN? Does everyone here know what a CNN is? Again, like, it's not a good question to ask. Okay. So why do you think we should be using a CNN? So CNNs have been shown to work well with images, and this is indeed image data. There could be some modern things you could use. So, but can you describe the whole process? Will you first go and collect such images from the internet, create a training data set? You'd roughly want equal number of images across the 3 classes of interest, and then you want to train a CNN model. What CNN architecture would you want to pick? Okay, someone else. What CNN architecture would you pick? Bhavesh? A bit louder. So he's saying that we will want to put some convolution layers and some pooling layers. So again, if these terms are sounding a little bit foreign, you'll have to brush up. Right? That's a part of the ML course that we have studied. But there are different kinds of layers: convolution layers, pooling layers, which we use in convolutional neural network. I'll put the references to the previous set of lectures for this particular example. But if you have to be successful in computer vision, you have, as Andrew Ng also says, pick up an architecture which is already working well. Right?
So we might even choose to perform transfer learning.
Okay, excellent. Excellent. So we may. Okay, excellent. So that's what I would now suggest given where we stand today in 2023. We should not be looking as training our own model as the first attempt. We should be using a pre-trained model. So a pre-trained model would mean that it's a model which has been trained on millions, billions of images by some large organization, let's say, like Google or Facebook or any such large organization. But they are generally trained on image data, but not on this specific data, which has 3 classes. They would have perhaps been trained on a dataset like ImageNet or CFAR 10, which have, let's say, thousands of classes, right? But we are looking at a 3-class problem. How do we reconcile? I will just try and show that. So imagine you have a pre-trained model. In this case, I'm just drawing something like a MLP, and you output, let's say this is 1000 classes, right? But now the problem at hand, we have only 3 classes. So what we do is copy and paste, copy paste, delete the last layer, put 3 nodes, right? And then make the appropriate number of connections. And in the simplest setting, you assume that, let's say, most of these weights are fixed and these are fine-tuned, or they are updated for your problem. Right? So if I again repeat, if you look at the top example, that has been trained on millions of images for 1000 class classification problems. So therefore the output node will have 1000. So the output layer will have 1000 nodes. But that doesn't work for our problem, and we don't have those 3 specific classes, let's say, in this 1000 classes. So therefore we have a new data set which has only 3 classes, we'll say that we'll use the same network as before with all the same set of weights, but we want to, let's say, modify only some small number of weights. We would typically perform this update or fine tuning on the last layer or last few layers. Why is that? Why not on the initial layers? Yes, Utkarsh. Okay. Okay, excellent. So if you remember in CNN, what we discussed in the ML course was that the initial few layers, we could think of them as feature extractors. Like they would be trying to look at things like, can we identify a nose, a pair of eyes, can we identify hair, right? So those things we'll assume are, those feature extractors are required irrespective of your three classes or any number of classes that you have. So the feature extractor part remains the same, but now you have three classes. So now you want to fine tune what a cat is. Cat is 0.1 times of dog eyes plus zero point 0.8 times cat eyes plus zero point 0.3 something, so on and so forth. Right? So once you have identified these features, how do you activate them to maximize your chances of correctly predicting on the three classes? Is the purpose behind using transfer. Right? For this problem, then we would be using something like transfer learning, more or less. We could have trained a model from scratch also, but we generally don't do that. Can anyone answer why? So one could be computational capabilities. You don't have enough computational capability. The second is you don't have enough data. Like these models have been trained millions of images. Maybe you have only thousands, 5,000 images. Right? So you won't be able to learn a lot of very good feature extraction. Okay, so let's say we used VGG like network. We had, let's say, 1,000 odd images for each of the class, and we did transfer learning, which means we just update the weights of the final few layers, and then we want to make predictions on new unseen data. So let's do that as per this blog, and this happens. The author, so because the author has put this image, that is the only reason I am putting this, but otherwise I would not have put this image. The author puts his image into the classifier, and the classifier predicts it's a dog with a probability of 0.98. The classifier gives an actual dog image and is predicted that it's a dog with a probability of 0.95. What has happened? Is there a bug in the code? There could be a bug in the code, but what else could help reconcile this set of results? Just one second. So how, due to transfer learning, are we likely to see a human being predicted as a dog? Okay. 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 So you're hitting in the right areas, but it's not exactly pointing out to what is causing the problem. Yes.
Maybe it has learned, like it has become a little more sensitive towards a particular feature, which could be just eyes, right? Like if it's getting eyes, it's predicting it as a dog.
Okay. Okay. So your answer is similar to Ritik's answer, that perhaps it is maybe only trying to see that this person's eyes are similar to dog's eyes, and it thinks that this is the case. I'm not sure. We'll have to use some activation. We'll have to use some visualizations to understand if that is the case. Yes. Okay. So Bhave says that we have only three classes. So every image that you give, which is of an appropriate size, will be classified into one of these three classes. So you have explained a part of the problem, but why a probability is 0.98? Why not 0.33? So would 0.33 have made more sense? Yes, but why not 0.33 but instead 0.98? Yes. Okay, excellent. So what he's saying is that perhaps the model is not even looking at the foreground, but is looking at the background. It could be that dogs are found in certain backgrounds, the cat are found in certain background, and wild animals are of course found in the wild, so close to nature. May not be the case. Let's assume that's not the case, and the classifier is indeed looking at the foreground. What could still explain the fact that a human being is predicted to be a dog with 0.98? Okay. Mhm. Okay. 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 Again, I think you're hinting at the right areas, but perhaps just missing certain important keywords to make the answer very crisp. Yes, Utkarsh. Okay. Okay. Okay, so that's one plausible explanation. We don't know how likely that explanation is, but that could be one plausible explanation. Anyone else? Okay, Mihir, you were saying something. Okay. Okay. So Mihir says an important keyword that neural networks are overconfident. Right? What do you understand when you hear that phrase? Neural networks are overconfident. Overfitting and overconfident could be two different things, but that's a good guess. That's a good first guess. They're overfitting. Someone else? The model complexity is indeed too high, but that's more related to overfitting than overconfidence. So first things, let me ask again. Uh, if it were not overconfident, right, we might have seen certain lower probabilities, right? And can we also say that this particular human being can be considered as not belonging to the distribution of the three classes, right? So therefore, this object can be seen as something which is out of distribution, right, based on the images that we have seen. So what is now happening is that the neural network is, with a very high degree of confidence, making a mistake on something which is out of distribution. Right? It has never seen anything like this during the training process. So we've detected one important problem. Neural network-like approaches are very susceptible to making mistakes on the distributions of data it has not seen. Okay? But perhaps the distribution of data of what does distribution of data of a human being mean versus a cat versus a dog is a little too sophisticated to understand. Let's try and see the same concept with a simpler example. And then we'll come back to how we can address this problem. Okay. Does anyone know this data set? Have you seen this before? This is the moon's data set from sklearn. You have two crescent-like shapes. So now this is, you have two classes. We're trying to learn a binary classifier. Right? And what we've labeled here is some out of domain, out of distribution kind of data. Right? So why do you think this is called out of domain? Why might you say this as out of domain? Okay. Other answers? So let me ask you a simpler question. So what kind of a classifier would you want to fit on such data? Two class classifier. Can you give the simplest two class classifier you may want to use? Logistic regression. What is the decision surface of a logistic regression? Is it a line? Is it a cube? It's a linear function, right? So if you were to fit logistic regression to this data, would you see a classification boundary like a line, right? Can you make some changes to the input or the features or the way logistic regression is applied so that you get a better fit? Can you do something to get a better fit? What could be that thing? feature.
Feature degree.
We can do feature expansion via polynomial, if you remember polynomial basis expansion, right? Again, in the ML course, we saw that if we are given in a regression problem, we could fit x, if we have a function and it's not linear, we could perhaps fit x square, x cubed as the input set of features. So again, we have two features. Perhaps we can expand the feature space. We can get a better fit via logistic regression. Right? Let's try and do that. So we use logistic regression and we get this figure. So all of these points are below this line are predicted to be below this surface, right? Not a line. So we can still use logistic regression and get such a non-linear like thing, although this is still linear, but in the transform feature spaces. So we see that all of this zone has a probability uh, of zero, of class zero, right? So this says that this is class zero. All the points here are class zero. All the points here are class one, and in a narrow zone in between is where you have a very rapid change of probability distribution between the two classes. So this is showing the probability. So if you look at the colors, they're trying to denote the probability of class one. The probability of class 1 in all this zone is 0, the probability of class 1 in all this zone is 1, and the probability of class 1 in this zone rapidly changes from 0 to 1. Right? So now what can you say about the probability of class 1 for this red set of points? It is 0, which means it is classified as class 0. Right? Do you think that's correct? Why not? That's what we've been doing in the machine learning course. We fit a linear classifier, or if we need, we expand the feature set by a basis function, but it's still a linear classifier. And it looks like a good fit. We're able to clearly separate out these two set of points. But here we are again saying the same prediction. Why do you think that's wrong? Sorry? Why do you think it should have low probability for both the classes? Okay. Okay, Utkarsh? Okay, excellent. So the data set that we have trained is these set of points and the above crescent, the two crescents. And for these set of locations, we are very, very far from whatever we've seen in the past. So we could think of that as we have something which we have not seen earlier. We should not be very certain of things which we have not seen earlier. Right? In this case, it's just saying everything below this, class 0, everything above that, class 1. Right? In an ideal case, we would have something different. We don't know that. We don't have data there. So that's the whole point. We don't have data there. If we had data here, which was again orange, and this was again predicting this to be class 0, we would be happy. But we don't have data. The closest point is quite far away. So if we look at the distance between the red and the orange, and the farthest points, and if you look at the distance between the farthest points and the crescents between orange and blue, they are comparable. Right? So in this amount of distance, we have moved from, so in this amount of distance, we move from the orange to the blue class. But in the same amount of distance, in fact, more amount of distance, we are saying it remains to be the same class. So that is the whole source of out of distributionness for this example. We don't know. So this course will help us appreciate the fact that modern day networks, they're not directly capable, or they don't express directly what they don't know. But that's the whole point. We need to know when the model doesn't know. If we just, sorry. So someone may argue that, but all you're trying to say is based on the distances, you should be saying that I don't know enough. Right? But if I am a little uncertain here, if you gave me a little more data here, I can be much more certain. But away from the inputs, I am not going to be certain. Like it's out of distribution example. Now, if you project this 2D example to the images, it's a fairly similar example. You have scenes classes of, let's say, cats and dogs, and maybe the human beings, when projected to this 2D space, are somewhere around there. So therefore, they are maybe just always predicted to be something like noise. Yes, Raj. I didn't follow your. When you train the model, we are using binary cross entropy loss, and then suppose for a point in the purple region. Okay, some point here. I am still. Yes. Mhm. Okay, so Bhave says that the loss function wants to separate out the two classes. That's not necessarily true. The loss function is ensuring that the points which are class 1, their output probabilities are close to 1, and for the others, the probabilities are close to 0. They're trying to do that, and then we naturally come up with the binary cross entropy loss. Okay. So the loss will just is just going to look at the training data, right? And on that training data, it wants to do well. But this is not a part of the training data, and it's very very far from training data. So both the things. If it was not a part of training data but close to the training data, we would get similar kind of behavior. But the important point here is that we don't know about this. We are so far away from everything we know. So that's the important thing. And we want to be able to then project this image back to the dogs versus cats versus wild example. The human beings are perhaps in a 2D sphere, 2D space if we were projecting. They are quite far away from the cats and dogs and everyone. But maybe in this 2D space, they're probably closer to dogs than cats. Right? That's why the model is making a mistake. In contrast, let's look at a more sophisticated model which has uncertainty built into it. What do you think about this model now? It's a very sophisticated model. It's a class of model called Gaussian processes. Here, if you see, it's saying that in data points close to the orange points, the probability of belonging to class 1 is 0. Right? So it's class 0. Whereas for the blue points, the probability of belonging to class 1 is very high. But in all the space which is in the giant universe of space about which we don't know anything, the probability of class 1 is almost zero point 0.5, right? Which is effectively trying to say we don't know at these set of points. Right? So we've seen one very simple example of cats, humans, dogs, and where we have been able to see that neural networks or approaches which have not incorporated uncertainty well, they will give us very wrong predictions, which are overconfident. Right? But had they given a prediction like 0.33, it would have perhaps been okay. Right? So we need to deal with this overconfidence problem, understand why this is occurring, and at the same point, this is a still more or less a very contrived example. Right? Imagine if you were using a similar kind of a neural network to detect, let's say, some particular heart disease. Right? The doctor needs to look at the output of the neural network model. It tells whether or not you should be doing a bypass. The model says 0.99% bypass is required. But that specific participant was perhaps of a different race, different gender, different age, and your model had again not seen any data like it. Right? So imagine someone having a bypass surgery when they didn't need it because the model was not smart enough to say that I don't know. Right? So medical application is one such example where you need to be very particular about not just quantifying your predictions, but also quantifying how certain you are about your predictions. Right? Can anyone give me some other example where you may want to be very careful with what the output from the model is? Stocks. Let's not get into stocks and things which are very hard for machine learning models to, in the absence of a lot of information to model. Can you think of something simple? Okay, military applications, whether or not you should be throwing a missile at uh, some warring country, right? Maybe you detected, your systems detected that an enemy ship is in your area or an enemy flight is in your area, and you just launched a ballistic missile. Later on, to realize that that was actually some bird. Imagine the political scenario then. What could happen?
autonomous transportation.
Autonomous transportation, Tesla, like autonomous cars. And there's a very nice example, I don't have it right in front of me. A Tesla was driving down the road. It sees a bullock cart. It thinks it's a car. Then it changes its decision. With very high chance, it says that perhaps it's a person. And then it changes its prediction to say perhaps it's a bike. Right? So it gets confused. It had never seen bullock carts earlier. Now imagine the state. It assumed it to be a car, and it would have perhaps assumed that the car would be moving at a certain speed. But it's a bullock car. Perhaps it can't go at that speed, so maybe it just goes and crashes. Right? But perhaps it just needed to say that I don't know. Right? Other examples? Yes. Sorry. Aviation sector. What are you trying to predict there? Okay. So the weather forecast, so he's putting the blame on the weather forecast, and which, like, a lot of people can put their blame on them that the monsoon projected does not occur when the on the actual date is delayed, or it's earlier, or the amount of rainfall is either more or less. Right. So he's saying that let's assume we take that to an extreme and the flight is taken off and it should not be taken off. Right. So how much confidence can you place in your models for forecasting, etc.? So in fact, for weather forecasting and things, and if you also look at Google weather forecast, there they ensure that a certain term which is known as calibration, your model output probabilities are well calibrated. So they ensure that. I'll not get into what that means. So, but in a nutshell, if I'm saying that the probability is 0.98, if I were to take, let's say, 100 such images whose probabilities are around 0.98, right, probability of class 1 being 0.98, if I take 100 such images, out of them about 98 should be actually class 1. That is the definition of a model is well calibrated. So I'll repeat. We'll get into the details at a later lecture. So this particular image has a probability of 0.98. Let's say we pick up 100 such similar images where the probability of class 1 or probability of dog is between, let's say, 0.95 and 0.99. 100 such images. About 98 out of those 100 images should be class 1. In that case, it's a good model. In this case, it's not clearly not going to be a good model because this will not look like a. We'll be able to find hundreds of images like this, which will not be dots. So we've looked into certain examples of why uncertainty is important and how networks can just make up stuff. They're just trying to predict based on the data that they have, and out of distribution is a big problem. Any questions? Yes. So his doubt, his question is that we have three classes. Let's add another class. I don't know. So these kinds of approaches can work. Either you could do it explicitly, or you could implicitly try and model all the sources of uncertainty, so that naturally you will get a output. Even if you have only three classes, you'll naturally get the probability of this being class one equal to probability of class two equal to probability of class three, approximately 0.3.
So it will never be enough. There will always be some things on which the model will be lacking.
Yeah, so we'll have, so let's, if we go back to the 2D example, we have a lot of space. Let's imagine an infinite space of which we know only very little. Right? So all of the remaining things are unknown. And modeling the unknown is not going to be easy if you explicitly try to model that. But there are better ways, more fundamental principled ways, all of which come through one equation in machine learning and Bayesian statistics, which is the Bayes rule. We'll see that in a bit, how everything we'll do in this course will start and end at Bayes rule. So we've seen certain applications now. Let's see if we were able to make the model better. So we have done something to the model now, right? And now it's saying that the probability of it being dog is 0.49, whereas the previous thing it said that the probability of dog was 0.98. This is before we did the change, right? Do you feel that this is a better model if this predicts that the probability of dog is 0.49? Yes. What do you think you could have changed in the model? Okay, I'll not answer this. This is a brain teaser. Hopefully, through the course of this lecture, we'll see some answers. Let's not answer this now. Sorry. Okay, so the question was that I've changed something in the model which takes my probability of dog go from 0.98 to 0.49. I've not changed the architecture. I have not done any wholesome changes, but I've tried to incorporate uncertainty into the model. Yeah, that has also changed. Yes. So I'll not answer this. I'll just want to have this as a food for thought for you. And let's come back to something else now. Okay. Do we have global warming? Do we not have global warming? Yes. Is the world warming up? I leave that to the experts. But if you just look at the amount of, at least the CO2 concentration is going up based on this data. This is taken from Mauna Loa. Where is Mauna Loa? Does anyone know? Hawaii. So these measurements of CO2 are taken from Hawaii. What can you observe about the pattern? Anyone else apart?
There is obviously like an overall trend of increasing the concentration,
Okay.
but like internally there is another like
Seasonality.
seasonality to the data. So the overall trend is increasing, but due to the seasonality,
Okay. Excellent. We can see two phenomena here clearly. One is an overall increasing trend. The other is some kind of seasonality. An ideal model would be able to model both of these, right? So again, as machine learning people, let's assume that this is a training data set given to us. We would fit some regression model to this, which we do now. So if you see the previous one of the measurements, in the red you see some machine learning model being fit on this data, and it seems to do a fairly good job. So machine learning models are generally known well to do well on, like you can have some very sophisticated models, like expressive models like neural networks, which will be able to fit very well on the training data set. But let's look at the problem. We want to project how much CO2 we'll see as an increase when we go forward. Why might we want to see that? Why is it useful to look at CO2 going forward? Future policies, current policies. There's the Paris Convention. There are various conventions, COP26, COP27, which happen around the world, where people come up with certain targets of how much reduction in CO2, how much reduction in temperature would that be able to bring forth. So we need some kind of projection.
in industry level, sir, all the manufacturing factories, they have to actually show some kind of certification that they have reduced some kind of CO2. So
Yes.
it have to be like volumetric. So
Okay.
knowing that CO2 concentration is increasing, that bar can could be is like the practice would have to work a little hard
Okay.
to lessen their concentration.
Okay, excellent. So he's talking about the carbon credit economy, that people have to exchange carbon credits, and we need to have good estimates of where we headed and how much temperature change and how much global warming and how much all of those effects are interrelated. So let's now project forward. Using the same model, I'm projecting forward. Does this look like a good prediction going forward? Why or why not? It's not one. It's not able to get the seasonal trends. Utkarsh? Okay. Okay. So the slope is slightly lower. So you may end up making the coal companies happier, or certain people, fossil fuel companies happier, that there's not a much amount of impact. What else are we missing? So let me ask this question in a simpler way. So today, if I take a poll and ask each of you what will be your grade in PML course, who can answer this with a lot of confidence? Anyone? Anyone? No. If I ask this question again, one day before the final exam, how many of you think you'll be able to answer that? Or what will be your final total? Not the grade. Most of you? What has changed? You've got some data about what else has changed. You're trying to do some projection, right? You are able to project sometime into the future, but it's very hard for you to project a long time into the future, right? So what is missing here? Just one second. The variance, the unknown, right? At this point, we are just saying that this is the overall trend, but I would be very sure about this value because it's very near to me currently in 2023. But 2050, I don't know much, right? I should have a larger amount of uncertainty. Now, can we relate this back to the classification problem, 2D classification problem? Regions very close to my training data, I should be more or less confident. Regions very far separated out of distribution, I should not be very confident, right? And how do we express a lack of confidence? By having higher variance in our prediction. So a better way to show this would be to show not just the model output, but also the variance in our output. Now, how we get that, we'll see in a few minutes. But here we can very clearly see that as we're moving ahead in time, our forecasts are poorer, or we have higher variance in the forecast. Yes, Ritik. Yes. The question is, does the model predict the variance? We need to create models which will also be able to, which are capable of predicting the variance. And at the same time, we also want models in such a way that the variance should be explainable. In this case, the variance plot looks okay. The further away we've gone from the data, variance is high. Any questions on this? Okay. So, who knows this person? Yes, Ritik. Both these people do not exist, right? Why are we studying this in the context of this course? Because probabilistic machine learning gives you tools to do some generative modeling. These are generative, these are outputs from some generative models. And if you again want to have fun, if you've not seen this earlier, each time you refresh, you'll get a very real looking person who does not exist. Right. So it's very funny to see the evolution of such generative models starting from the GANs. Right. So generative adversarial networks were the first modern class of algorithms which were looking at something simpler. And you may think that GANs is also doing this kind of stuff. But perhaps just let's go back and see the first papers. So interestingly, this has been cited by 59,000 people already, and less than 9 years old. So if you were to look at some of the images, okay, so these have been generated by GANs in the original paper. Contrast the quality of these images with what you just saw. Right? And what you just saw is not the state of the art. Sophisticated diffusion models where you can give a text prompt and you can create movies out of them. Right? They are more or less the state of the art. We're not, and in this lecture, we're not discussing how to do this modeling, but I'm just showing that you should be able to create such kinds of models using probabilistic generative models. Here at the top, you see the cliched MNIST examples, which was considered to be like the playing ground. You playground has to have a very simple set of examples, but the more realistic examples look very faded compared to what we have here. So this brings us to certain questions which we discussed in the machine learning course, and we should review them now. So in the machine learning course, we said that for something like linear regression, we want to be using squared error loss function. Why? Why do you think we use that? Sorry? We don't know what is MLE. I will be discussing that. Sorry? Okay, so he's answering about why, he's talking about the squared part of it. So the intuition which you study in the linear regression in the ML course is that you want your model to fit well to the data, and each time there is a residual error, you want to minimize the squares of them, right? But why squares? Why not power 4? Why not the absolute value? Why not something else? Right? The squares seem like a natural fit, seem like a very good intuition, a very good loss function, but perhaps there's a more mathematically inclined, more basic way of thinking about that, which we'll see in just a few minutes. Sorry, there's another point. So convex function. So convexity is to for mathematical convenience, but there are many more convex functions which could have used, including just the absolute value. We could have used that, but we mostly use squared error. Similarly, logistic regression, we use cross entropy. Why? It's a weirdish formula, right? So you have minus y log y hat kind of terms. Where do you bring log into the function? Like log into the picture. Why bring that? Why not keep things simple? Yes. So the mathematical convenience is of course there. So log is so the particular form of cross entropy loss is one of many such functions which would be mathematically convenient and which would satisfy what we want, right? When our prediction is 0 and the ground truth is 1, we should have a high penalty and vice versa. That's the main thing which we wanted, right? If the predicted point gives you probability of class 1 to be 0 and it's actually class 1, you want to put a high penalty. That is what the loss function is mostly trying to do. But why cross entropy? Why that particular form? We'll see in this course in just a few minutes. How many of us know what numpy.random.random does? It generates normally distributed random samples with certain mean and variance. But how does it work under the hood? Is it a deterministic algorithm? Is it a completely random algorithm? How does it work? In this course, we'll study how we can sample from various distributions. So this was something which we discussed in the ML course also. So if we have certain data X and we take the standard deviation of that through NumPy versus through Pandas versus through Torch, we get different answers. Why? Again, we studied this in the ML course, not the details. One of them is gives you an unbiased estimation, the other gives you a biased estimation. Again, these terms may sound a bit foreign. We will discuss them in the course, in this course. Right. So another question to whet your appetite. What is the link between Robert Oppenheimer and this course? Apart from the fact that the movie was released just a few days back, what is the relationship between them? I am not going to throw or create atom bombs. What is the relationship? Okay, can you expand on that? Okay. Okay. So a lot of the development for the atom bomb required some very sophisticated integrals and certain probability distributions and integrals, which were impossible or intractable. You could not compute them. So they ended up doing some certain simulations, certain approximations for them. Now they didn't have a very powerful computer to do that. If I have to do those kinds of things using a modern day computer, it may take me microseconds. They created certain systems for doing that, and that eventually gave them certain insights into what amount of critical mass to use and various other very sophisticated things about the atom bomb. So some of the maths developed during the Manhattan projects and similar things is being actively used, is going to be used in this course. So that's the relationship between Oppenheimer, the Manhattan project, and this course. So any questions till this point of time? Okay, I'm going to ask a question which some of you may have seen earlier, but I think it just gets it in the right frame of reference. This is the farmer or librarian example, and let's go over this. We know that Steve is a shy and withdrawn person and helpful, but doesn't have much interest in the people or the world of reality, a meek and tidy soul, and has a need for order and structure and a passion for detail. What do you think? Is Steve a librarian or is Steve a farmer? What do you think? We've seen librarians here and we've seen farmers or people in the horticulture department in the campus, right? Which of them would you attribute being closer to this? No, Utkarsh, you know the answer. Right? Anyone? Okay, how many think Steve is a librarian? Raise your hands. How many think Steve is a farmer? How many think it's 50-50? Okay. So anyone who thinks Steve is a librarian, by? You said? Yes.
Because of his physical features like farmer being a neat and tidy, so my need of order and structure is characteristic.
Okay. So neat, tidy, order, structure, you think of a library, very well organized racks of books. Shyam withdrawn, doesn't need to go much in the world, will quietly sit, will not speak much. The library is a very quiet place. So based on the characteristics, it seems very natural to think of Steve to be a librarian. Right? But someone said a farmer. Who said anyone? Yes. What do you think? So we don't know the number of farmers to the number of, we don't know the ratio of the librarians to the number of farmers. Right? It's possible that in this world, there are way more farmers than there are librarians. Right? So someone of this characteristic could be a farmer with a low probability. Right? You could out of, let's say, 100, let's pick up their numbers only. So the first thing I'm saying is that according to statistical data that they've collected, there are way more farmers than librarians in the world. Right? So does this influence your thinking? How? How does having more farmers change your beliefs about this person could be a farmer? Because this person is still not showing much characteristics of a farmer. Still very orderly, still very neat. How does this person seem like, how does knowing the fact that there are more farmers than librarians change your perception, your beliefs? Anyone? Earlier you didn't know about these ratios, but even after knowing these ratios, how does that help you? If you randomly picked up a, so So we forget about the fact, the description, right? And if you randomly pick up a Steve in the town, right, is that Steve more likely to be a librarian or a farmer? Farmer, because there are way many more farmers in the world. But of course, some description is given, right? And then we also need to see how much of the description fits farmers versus librarians. It's very obvious that that amount of description fits librarians well. But maybe there is still a small chance that the description fits farmers also. Right? So let's assume certain numbers. Let's assume that there are 20 times more farmers compared to the number of librarians in the world. Right? And let's take a small sample of 210 people. So in that sample with 20 to 10 ratio, we'll have 200 farmers and 10 librarians. Now, based on this meek, tidy description, we'd say that 40% of the librarians may fit that description. There may be some librarians who go beyond the obvious description, but 40% of them will fit this bill. Whereas with the farmers, maybe that's just 10%. There is a very small subset of the farmers. How does now knowing these 40 and 10% numbers and the fact that the ratio is 20 to 1 change your beliefs? Yes, sorry. Yes, ma'am. Yes. Yes. So we have a small, so this description fits only 10% of the farmers, but the number of farmers is huge. Right? While it fits a large proportion of the librarians, but the number of librarians is huge, or is small. Right? So if you were to take only this sample of 210 people, how many out of the 200 farmers do you expect would fit this bill now, would fit this description now? 10% of it, which is 20. How many of the librarians out of 10 would fit this description? 4. So therefore, if we were to look at 210 farmers, we'd say that 4 librarians and 20 farmers would fit this description, right? And that is what is being shown. So the probability that a random person who is going to fit this is 4 over 24 or 16.7%. So probability of librarian given this description is this, 4 over 24. And this is where you want to be now fitting the Bayes rule. Right? So what you just saw was probability of so we have 20 random person who fits this description is 4 over 24. Right? So just knowing the fact that Steve is shy, withdrawn, would take you towards what you've observed, right, which is known as the evidence. But what you're missing is a very strong prior information. In this case, which is going to dictate, which is the fact that there are a lot more farmers in the world compared to librarians, and this description, though, fits the librarian more compared to 40 is to 10 percentage ratio, but still the raw number of farmers is just going to outnumber this, and therefore if you were to do the calculations in the Bayes rule formula, this person would turn out to be much more likely to be a farmer than librarian. Right? So this is an important concept because generally we think in terms of the evidence which is given to us, but it's hard for us to think in terms of the prior that we have. Right? So can someone now tell me, relating to some real world examples or something in your life where you might think of applying Bayes rule in a similar sense? Disease one is a very cliched example, but I've been discussing this with the TAs. Should we put this disease example or not? So let's say you said that the probability, if you've tested positive, it's very likely that someone has a disease. Let's say 99.99%. Right? At the same time, 1 in a million people have that disease. Right? That should impact your beliefs, but will it? It should be very, like, you'll have to be a mathematician working with theoretical possibilities and afraid of all such rationality, afraid of, you'll have to be non-afraid of things which math can't explain. mathematical possibilities would reduce the chances of that disease because it's maybe 1 in a trillion people have that. But the test that you've done is very specific and you've turned out to be positive for the disease. But both these factors taken together would reduce the probability of you actually having the disease. Any other example you could think of? How do you decide to take courses? How do you decide to take courses? Can you think of a Bayesian perspective to it? Do you have a certain prior of the grades a certain faculty gives? Right? You may have certain observations about that faculty, yourself, about likelihood of yourself getting a good grade, your interest in the subject, and then you have to combine your prior, the prior that you've obtained through seniors, with some of your own observations. Any questions till now? So now we come on to why we are looking at the Bayes rule in this course. So this is the general definition of Bayes rule. Probability of A given B is probability of B given A times probability of A divided by probability of B. Now this is the most important slide in the entire course, and you can see why. So you'll see this slide everywhere for the next. You'll see this formula everywhere for the next few slides. So we'll be starting off with something as simple looking as the Bayes rule. Now we'll be putting the machine learning context to it. You have theta d as two different terms in this equation. In this case, I've replaced A with theta and B with d. I have four mathematical terms here. P of theta given d, which is known as posterior. So typically we start with going from right to left. Right? You have certain prior P of theta. Right? So theta is known as the model parameters. What could be the model parameters for a linear regression model? Let's assume we have a single input variable x. Model parameters would be theta naught theta 1, right? So your model is y hat equal to theta naught plus theta 1 x. So in that case, theta consists of two parameters. It's a vector of containing two numbers, theta naught and theta 1. We have certain prior on theta. What do you think that prior means? Sorry? So prior means that, so it's a probability P of theta, so it has to be distribution. We think that before we have observed any data, so the prior is before you have observed any data, our beliefs about theta are as per some distribution. We don't know about that. Once you've observed some data, once you have certain evidence, you have made certain observations, you want to now see which of the theta made more sense. Right? Initially your prior could be very weak, right? But once you've observed certain data, you want to update your prior, your beliefs about the parameters theta to something which is on the left hand side. Right? Prior, once you've observed the data, which is connected to something known as the likelihood term, you get the posterior. So prior, posterior, the thing which is separating them is observation of the data. Right? Any question about this now? We'll go into the details of what each of them is. Yes, Ritik. Can you use this? You will. So the question is, can we use this formula when we don't know the distribution from which the data comes? We always make certain assumptions about the distribution from which the data comes. So we incorporate that in the likelihood. We don't know. We're always making certain assumptions. Like we don't know whether the data is linearly fitted. Is coming from a linearly distributed data or not. But we make certain assumptions that the data is linearly distributed according to some linear relationship between output and input. And on each of our observation, we have certain amount of variability, which we describe via something like a normal distribution. Okay. Questions in this thus far? So let's start off with a simple exercise. We want to figure out the electricity consumption of the hostels in IIT Gandhinagar. Yes. Do we update E of D given theta? No. We'll see when we walk through this example. So think of theta as the quantity of interest in this case, the model parameters. Before you observed some data, this was your understanding of the parameters. After you observed some data, this is your understanding about the model parameters. So the task at hand is to understand the electricity consumption in the hostels of IIT Gandhinagar. So I'll be picking up one such hostel. Let's say I pick up hostel H. So this is the number of occupants, and this is electricity consumption in kilowatt hours. I have certain points, something like this. I would naturally think of modeling this with a linear like data, right? So let me give you a few options. We have three options, A, B, and C. Which of them do you think is the most likely explanation for the data? A, B, and C. Which of them is the most likely explanation of data? C. Why do you say that? There it seems to fit the best. So what we're trying to say is that can we pick up certain models? So with each of them, I will write this as theta naught B, theta 1 B, and corresponding to A, theta 1 A, sorry, theta naught A, theta naught C, and theta 1 C, right? So we're trying to figure out certain parameters, certain theta naught and theta 1, which explain the data the best, right? Or which will likely explain the data the best, or which are trying to say, or which are trying to maximize the likelihood of observing the data given these parameters. Right? I'll repeat that. If a model parameters, let's say that the model parameters are corresponding to C, are we likely to see such a data set? If the model parameters are corresponding to C, which is theta naught C and theta 1 C, are we likely to see such a data set? Very likely. If a model parameters are theta naught B and theta 1 B, are we likely to see such a data set? No. Why? One, we see that there is an increasing trend as the number of occupants increase, the electricity consumption increases. Secondly, it seems to have a very high offset. Right? So both of these factors seem very inconsistent with the data, which means that our probability of observing the data given the parameters theta naught C and theta 1 C is much, much higher. Right? So our data at this point, is xi, yi pairs, right? Which is number of occupants 1, comma electricity consumption 0.1, OCC 2, right? So this is your data set. We go back to the Bayes rule. We had written that probability of theta given d right. So we'll be writing this rule again and again throughout this course. Let's just look at the first term. Just look at this term, p of d given theta. So how likely is the data to have been generated from these set of theta values? We have very clearly seen that in this trivial example, it seems that it is much, much more likely that the data was generated using C compared to B, right? But our aim is not to do a comparison in a discrete world of is C better than A, better than B, better than D, better than something, right? But rather use a powerful tool of optimization, right? So what we end up doing is we end up saying that we want to figure out some theta which maximizes this particular quantity, right? So don't worry if you don't understand all of these terms or how do we calculate P of D given theta, what does this expand to, right? Those things we don't need to know. But let's just for now, for this class, understand P of D given theta as the probability of observing the data given these parameters. In the simple three examples, it's very clear to us that if these are the only three choices given to us in a discrete set of questions, we would pick up C, but there could be infinite such possibilities. Right? Out of that infinite possibilities, we want to use optimization and say that figuring out the maximum likelihood estimate, where this particular term is known as the likelihood term. So this is the likelihood term. You're trying to find an estimate of theta which maximizes the likelihood, which maximizes the probability of observing the data given some theta. Right? What theta is most likely to have generated this data is what we're trying to find out. Right? Interestingly, if we expand this out, which I'll do in the second or the third lecture, for linear regression like problems, this will be equivalent to so this will come out to be yi minus yi hat square, right? So this is the expression which we have seen earlier, where we write yi hat to be xi transpose theta, right? This is the expression which we saw in the previous course, and this is the expression which we're seeing in this course. If we expand or work out the maths, they both give you the exact same answer. Right? Now, in this derivation, we will not be considering squared loss, but we'll end up as a consequence of maximum likelihood estimate to get the squared loss as the loss function. The question. So in this lecture, I'll stop at this point, but I'll just give you a sneak preview of what we're going to do. We'll continue with this example of electricity prediction. We'll quickly walk over it. We'll see that, so we have this expression of what P theta given D is. Just look at the different problems which we can solve and how they map back to the classic conventional machine learning that we have. Theta MLE maps to the conventional just fit a loss to some so optimize the loss function according to some loss that you have chosen. So that's the first problem which we have done. This would lead to cross entropy for the classification case. Second is known as maximum a posteriori. The previous case you maximize d given theta. This case you maximize theta given d, which is occurring on the left hand side. If you do this, you see that it's argmax of two terms multiplied. This leads us to the same result as regularized models, loss plus penalty. Right? You've seen that earlier. It's just a more unified framework for doing that. Third, we will not just be looking at a single value of theta, right? Theta MLE, theta MAP are single values of theta, just one value, 2.1, 4.0, something like that. But can we have entire distributions of these? Theta is distributed as a normal distribution with certain mean and certain variance or covariance in the multivariate case. That will come as a consequence of, again, the base rule. We will then look at one main challenge of this integration. Right? Similar problems in a different context what I was discussing about in the case of atom bombs. So again, we encounter various intractable integrals which we can't solve. We therefore we don't solve for this exactly, but we still try and get some approximations for p of theta given t using something known as variational inference, something known as Gaussian slash Laplace approximation, using something known as sampling methods, which is what a lot of atom bomb people would have used. And then we look at how to get the uncertainty in our predictions. Once we have learned the uncertainty in the parameters, so once we've learned the uncertainty in the model parameters, we want the uncertainty in the predictions. So we'll see throughout the course how these same set of equations will come over and over again. Okay. I'll stop here. Any questions? Okay, so all of you, I'm requesting you to please join on the Slack channel because the further communication will happen there. And Mihir wants to put a poll on changing the class time. Okay, thank you.